Let's take this another problem. Once again, it's a very small problem, but I'll tell you. We find the moment of inertia of a uniform square plate of mass m and age a about one of its diagonals. Now, this particular deduction, that moment of inertia of a square plate about one of its diagonal, is normally not given in many textbooks. I told you while discussing the theory that you should practice all the deductions from your textbooks and you should also remember them to answer all the possible numerical problems. But this diagonal was not given in many textbooks, so I thought I'll do it for you, and it will be needed for us. We shall need it also to solve some problems of your exercises. So it's a square plate. So let's take a square plate. Let's take a square plate here. Let's take a little bigger so that you understand it properly. So this is a square plate, and we have to find out its rotation. We have to find out its about its diagonal. So this is perfectly a diagonal. So what they say, the body is rotating about its diagonal. So diagonal is the axis. Once again, as I promised you, this problem is not a difficult problem at all. First, let us see what is given. Mass is given m, and also is given age is a. So all of these ages are a, 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 a. If I divide this by another diagonal, then you see I have 4 identical triangles, and all are right-angled triangles, right-angled and also isosceles triangles. So the problem becomes very easy. If I can find out the moment of inertia of any one of this triangle, any one of this, let's say this triangle, let us take a shading of this triangle. Let us take a very light shading of this triangle. Let us consider this triangle. If I can find the moment of inertia of this triangle, and then the total moment of inertia will be only multiplication of that answer by 4, because all other triangles are symmetrical along the axis, symmetrical around the axis. Now, taking this first triangle, you see this height is a by root 2. I don't have to make the deduction for you. You understand. This arm is also a by root 2, right? Now, what do you do? Now, from here, we go to a distance of x and take a very thin slice of thickness dx. Now, from the simple geometry, you know, if the distance from here to here is x, then distance from here to here is also x, because this is an isosceles right-angled triangle. So, length of this small section or thin section is actually x, right? So, consider, we put it this way, consider a thin section at a distance x from O, say, from O. Let us say this point is O. The height of this section also x. How I get it? From simple geometry. I write it from geometry. Is x. And thickness of this section is thickness of this section is dx. So area of this section is equal to x dx. Height of this section x multiplied by this section dx. Area of this section is dx. Now, we go to the other way. We go to the second point, that total area of the square plate is equal to a square, because it is given each side is a, and its mass is equal to m, that is also given. So mass per unit area is equal to m upon a square. M upon a square. So mass of the thin section taken, for calculation is equal to mass per unit area is m upon a square multiplied by area of this thin section is x dx. So this is the mass of the thin section, and its distance is also equal to x, because we have taken it at a distance x, right? The same thing will happen if you consider it calculating from the axis side. Now, therefore, so moment of inertia of the thin section is equal to, its mass is m upon a square x dx. And, oh, by the way, you remember the moment of inertia of any thin rod of length L and mass m around the axis but passing through its edge is given by ml square by 3. ml square by 3. This basic moment of inertia calculations you need to remember, ml square by 3. So here the moment of inertia is m, its mass was m upon a square into x dx, and L square by 3, and its distance is, its length is x, so x square by 3. This makes m by 3a square x cube dx. The process is always same. You have to always find out the moment of inertia of any small element and then do the integration. So this is the moment of inertia. And what is the limit? X tends from A to 0. A 0 to A upon 2. 0 to A by root 2. So total moment of inertia of this sector, this triangular sector, moment of inertia of this triangular sector is m by 3s square integration of x cube dx from 0 to a upon root 2. 0 to a upon root 2. This is equal to m by 3s square, and its integration is x to the power 4 by 4, and its limit from 0 to a upon root 2, a by root 2. This is equal to m by 3s square, we write as usual, m by 3s square multiplied by this 4 we take outside, multiplied by 1/4, multiplied by x to the power 4, and a value of the x in the limit is a by root 2. So this is equal to a to the power 4 by root 2 to the power 4 is 2. Right? So what we have? This s square gets cancelled here. What we are remaining with s square. So this is equal to m upon 3s of 4, 12, 3s of 4, 3s of 4. So this is, sorry, this is s square by 4, root 2 multiplied by, I'm sorry here, not s square by 2, this is s square by 4. Because it is root 2 square, root 2 has to be raised 4 times, root 2 to the power 4. So root 2 into root 2 is 2, 2 to the power 2 is 4, 4. This is equal to m upon 3s of 4, 12, 12s of 4, 48. M upon 48 s square. So this is the moment of inertia of one triangle. So total moment of inertia, so total moment of inertia of the square plate is 4 times of this. This is 4 multiplied by m by 48 s square. This is m s square by 12. This is the answer. So the problem is not difficult at all, but I thought I would make a practice with you of how to deduct the moment of inertia of any body. And it should be a regular body, because if it is a totally irregular body, the integration becomes very, very difficult. Okay, now let's go to the next problem.